Welcome to the presentation on a hybrid encryption technique based on DNA cryptography and steganography by Shahriar Hassan, Mohammad Asif Mustafa, Mohammad Shohrab Hussain from Bangladesh University of Engineering and Technology, and Husnu S. Norman from Marshall University. I am Shahriar Hassan presenting this to you. This presentation is prepared for 13th IEEE Annual Information Technology, Electronics and Mobile Communication Conference 2022. So let's start. As the world is moving towards online services, secure data transmission is becoming a serious concern. Data encryption and data steganography techniques are employed to ensure data security, but the challenge is to find a specific algorithm that encrypts and hides data in such a way that it doesn't get intruders' attention. In this work, we propose a secure hybrid data encryption technique using DNA cryptography and steganography. So DNA will be used for both encryption and hiding process. The reason behind using DNA for encryption is that we can encrypt any message with only 4 DNA bases: adenine, guanine, cytosine, and thymine. And also there are 163 million of DNA sequences publicly available. So it is also convenient to use for steganography techniques. Our objective is to propose a robust model of data encryption so that data can be transmitted securely without getting attention of the intruder. We analyze the security of the proposed model and to provide a comparative analysis with some related works. Our outcome will be a blind, symmetric, DNA-based encryption and steganographic technique which have a decent cracking probability. Our proposed approach will help secure data transmission, especially in banking, e-commerce, authentication, and client-server communication sector. Let's discuss some related works. Namdev et al. In 2016 proposed a DNA and amino acid-based approach with Playfair cipher. They first encrypted their message into DNA sequences and then further encrypted by a 4-square encryption process based on amino acid structure. Hence, they didn't use any steganographic technique, and so the technique gives only a single layer of protection. Now we'll discuss some techniques that only use DNA steganography. First, Xu et al. Compared 3 techniques of steganography, that is insertion, complementary rule, and substitution, and they showed that substitution is more convenient. Guo et al. Proposed a substitution-based method in DNA sequence for message hiding. They basically explored motifs in DNA sequences and substituted that motifs with message bits. Yunus et al. Also proposed a motif substitution method in DNA sequences, but this technique is not blind. Also, motif substitution technique has higher modification rate. Hamed et al. Proposed complementary rule-based DNA steganography technique, but this technique doesn't preserve biological functionality. Mousa et al. Proposed a reverse mapping-based method in DNA sequence for message hiding. This is basically a substitution technique. Now we'll discuss some hybrid techniques. Mitras et al. Encrypted their data with RSA algorithm and DNA encryption, and after that they used insertion method to hide the encrypted message into DNA sequences. But insertion technique basically extend the real length of the DNA sequence, so it will get the intruder's attention. Tor et al. Employed 5x5 Playfair cipher technique for data encryption, and they used insertion method for data hiding. Playfair cipher generates ambiguity bits, and we need to send the ambiguity bits separately. Yadav et al. Encrypted the data with DNA encryption and used images for hiding that data. When images are used for steganography, the resolution of the images are changed, so it will get the intruder's attention. Now we'll discuss about the proposed method. We have 2 phases: encoding the data using DNA encryption and hiding the data in real DNA sequences. For DNA encryption, we use 2-bit binary encoding techniques, and also we employed Huffman coding for generating the variable length code for the DNA bases. That will add more security for us. Then for data hiding, we used a modification of 3:1 LS-based substitution method. In this method, we change the nucleotides after every 2 nucleotides from the beginning of the DNA sequence according to the encrypted message bit. Let's understand our technique with an example. For example, we took a plain text P, that is hello, and we converted it to ASCII value, and we get the P bin. Then we will take each two digit from the left and convert it to the DNA basis according to the 2-bit binary encoding rule. We got a DNA sequence M, and we will calculate the frequencies of the DNA bases in the DNA sequence, and with the help of Huffman encoding scheme, we will generate variable length code for all the DNA bases, and finally substituting those DNA basis code, we will get the ciphertext mbin. Then for data hiding, we will first collect a DNA sequence D from NCBI database, and then using the 3:1 substitution rule, um, according to the mbin value, we will change the bases. So if the base is a purine base, that is A or G, and mbin value is 0, then we will substitute that value with A. Otherwise, we will substitute with G. And if the base is a pyrimidine base, that is T or C, and the mbin value is 0, then we will substitute with U. Otherwise, we will substitute with T. So thus we will get the final ciphertext DC, but we need to send the Huffman code with it, as there are only 4 DNA bases and Huffman code will be same, but the order will be different. So we need only, we send only the order sequence as the key. We need not to send it separately. We substitute the first, second, fourth, and fifth nucleotide of the sequence with the order of the DNA bases. And this actually provides more security to our method. So this is the full proposed method. In the receiver end, when we decrypt the message, we just reverse the encryption technique and we get the final message. For implementation, we used Python programming language on a Core i5 and 8 GB RAM system, and we took a text message containing letter, digits, and symbols in a 5 kilobyte file. We encrypted the text messages and hide it in 8 real DNA sequences of different length collected from NCBI database. Then we investigated capacity payload bit per nucleotides, encryption time and decryption time for each DNA sequences. Also, we derived the cracking probability of our proposed model and done comparative study with some recent works. These are the DNA sequences from the NCBI database, and we can see the length of the DNA sequences are increasing from top to down. The experimental result shows that the capacity of our proposed method is 1/3 of the length of the DNA sequences, as we do not increase the length of the DNA sequence, so payload is 0. And as we use 3:1 substitution method, so we need we need 3 times larger DNA sequence for sending a message. So the BPN is near 3 in our experimental result. And if we plot the encryption and decryption time in a bar chart, we will find that time is increasing with the increasing length of the DNA sequences. Also, the decryption time is less than the encryption time. Now, the security analysis. If one wants to break our security, then he needs to know, first he needs to know the DNA reference sequences. But there are around 163 million DNA sequences into the public database, and the first 6 bases of the sequence might be fully changed in our model. So intruder needs to analyze the rest n-6 bases of a DNA sequence. Hence, the probability of guessing correct DNA sequences is 1 by 163 million into n-6. Then he needs to know the what binary encoding rules was used. So there are 4 symbols, A, T, C, and G, and there are 4 options for binary encoding, that is 00, 01, 10, and 11. Also, there are 4 Huffman code option, that is 000, 001, 01, and 1. So the probability of guessing the correct code each time is 1 by 4 factorial into 4 factorial. Then he needs to know ls-based substitution rule, as there are two options for purine based substitution and two options for pyrimidine based substitution. So the probability of guessing correct substituted nucleotide is 1 by 4. So the total system cracking probability is 1 by 1.63 into 10 to the power 8 into n minus 6 into 4 factorial into 4 factorial into 4. That is quite decent cracking probability. So here we have compared our proposed method with some of the related works. We used 11 comparison criteria we found in different literatures. If we summarize the findings, we see P3 and P4 employed only steganography techniques, hence only single layer of protection and high cracking probability. P1, P2 and our proposed method provides double layer protection, and P1 and P2 also have lower cracking probability, but they have high modification rate, payload, and doesn't preserve biological functionality. On the other hand, our method is blind, zero payload, low modification rate, and preserves biological functionality. So in the conclusion, we summarize our work. In this work, we proposed a novel cryptographic technique combining DNA cryptography and steganography. The techniques encrypts the data in its first stage and then hides the encrypted message into an actual DNA sequence. The encryption method uses DNA bases to encrypt the messages, followed by a variable length code generation and assignment for each DNA base using Huffman coding. The proposed method is blind and it doesn't expand the actual DNA sequence while keeping its biological functionality. Experimental results and analysis shows that our proposed method gives a decent level of security, which is quite impossible to break without having full knowledge of the steps involved in particular encryption. Our proposed method can be modified in our future work to increase its data hiding capabilities and security. So these are the references used in our paper. Thank you.